some of the stuff we've talked about on other things. Domain, range, concavity, increasing, decreasing, end behavior, those sort of things. And we're going to look at how those are the same and different for log graphs. What's going to happen for this is everything is going to be a little bit switched from the way it was with exponentials. So when we were talking about exponentials, they always had a horizontal asymptote. Well, logs are always going to have a vertical asymptote. We might, and I don't know that he puts that there, so we might want to add it over here. So we can add in a little note right here. Exponentials have a horizontal asymptote. Logs have a vertical asymptote. Okay. Exponentials, unless they've been shifted up or down, exponentials are always, our y value is always positive, right? So unless we've shifted them up or down or flipped them upside down, exponentials always have a positive y value. So for a log function with a base that's larger than 0, I don't think we're going to see negative bases on logs at all. I don't recall ever seeing those. I guess it could happen, but I don't recall seeing those. In this equation, where the base cannot be 1, we're never going to see a log base 1, because what is 1 to any power? 1 to any power is just 1, right? Like, well, it's still 1. So, like, even to the 0 power, it would still be 1, right? So 1 times itself 1,000 times is still 1, right? So we'll never see a log with a base of 1, so that's why it says the b cannot equal 1. You're not going to see that a equaling 0, because if this number out front equals 0, what does the whole expression equal? 0, right? So you're always going to have a number out here. But if we have a log function of this type, our domain is going to be 0 to infinity. That vertical asymptote is going to be at 0. Right? So on this graph right here, we can see both of these. We got a vertical asymptote at x equals 0 for both of these. I said we won't see negative bases, but I guess technically you could. No, that's just a is. So if a is greater than 0, if you have a positive number up here, this is what your log is going to look like. Yeah, you just said it there. For this, this is what your log is going to look like most of the time for this. Whenever you have a positive a, if I put a negative in front of it, it just flips that graph over the y-axis, and I'll get a graph that looks like this. So this is the shape that we're going to see. Think about what the exponential looks like here. If I think about putting, the line y equals x right through here, right, and I think about reflecting this graph over the x-axis, what I end up with is a exponential right here, because they're inverses of each other, right? So, so the log is going to have a vertical asymptote at 0 unless it has been shifted, and it is going to be the inverse of an exponential. So whereas an exponential starts off growing really slowly and then takes off really fast, a log is the opposite. It grows really fast at first, and then it slows down after that, okay? So much like exponentials, logs are always increasing or always decreasing. They are not going to switch from increasing to decreasing. So you do not have any local extrema. So you're not going to have any relative maximums on a open interval. If it is on a closed interval, technically the endpoints can be your relative maximum minimums according to this. But you're probably not going to be asked about that. So you're always increasing or always decreasing. The graph will also always be concave up or always be concave down. So this might be one of those things, some of those questions on the test where it told you like A is greater than 0 and B is greater than 0 in an exponential. You might get that same sort of thing but with a log, right, to be able to tell increasing, decreasing, concavity, those sort of things. End behavior for a log is going to be a little bit different, okay, because whenever we look at a log, here, on the right side, x can approach infinity, right? X can approach infinity, and as x approaches positive infinity, you will get positive or negative infinity, always. Actually, both of the answers here are going to be positive and negative infinity. But look over here at this limit statement. It's different. This is our left side limit statement, right? So this one here, let me switch colors back. This is our left statement right here, and this is our right statement. The right one looks like everything else we've seen, right? What's different about that left side limit statement? It has x approaches 0, and it's got a plus sign behind it, which means from the right. So why do they have that instead of negative infinity? We've got a vertical asymptote at 0, right? Is my graph ever going to go past 0? No. So is it ever going to approach negative infinity? It shall not, because it's never going to go below 0, right? So when we talk about log graphs, and we're talking about that left side, it could be the right side if they reflected over the x-axis or the y-axis. That's not going to happen very much. But when we're talking about usually the left side, we have to think about where that asymptote is at, right? Because we are approaching that asymptote, not negative infinity, right? So you're going to see this be different. It's going to be 0 most of the time unless you have shifted the graph left or right. Because if you shift that graph left or right, it's going to shift the asymptote as well for that. So let's look at a couple examples right here. So notice right here, he's helping us out a little bit. He's doing our limit statement for us here on the left side. He said the limit as x approaches 0 from the right. That means that we are looking at this line right here where x equals 0, and we are approaching that line from the right. So we're starting here and we're going to this line. We can't go past it because it's an asymptote. Where are our y values going as we get closer and closer to that vertical asymptote? Negative infinity, right? Because you're thinking y values, not x values. X values are going to 0, but y values, we're going to negative infinity. The right side is going to be, like always, limit as x approaches infinity of f of x. And what will we get on the right side? As we trace this graph going to the right, what are happening to our y values? They're going up. And sometimes on a log equation, it's going to look like it has a horizontal asymptote. Let me give you an example here of this. Let me go to Desmos and let me type in just y equals natural log of x. All right. If I zoom out pretty far, that sure does look like it's got a horizontal asymptote to it, doesn't it? But logs never have horizontal asymptotes. Exponentials have horizontal asymptotes. Logs have vertical asymptotes. So if you see that you're increasing, even if it is very slightly, right, you're going to positive infinity. Because logs whereas exponentials grow slowly at first and then take off growing very quickly, logs are the opposite. They grow quickly at first and then they grow very slowly. So although you are not growing very fast, it is still growing. So like that looks like it's about x equals 5 or y equals 5. That looks like such a good asymptote for that, doesn't it? But if I drag this over here, it eventually crosses it, that red line one on top. And that would be the case for everything. It's almost like you guys can't use Desmos in the calculator. You're not going to be able to see it well enough to look at that much anyway. But I just wanted to point that out because these do sometimes look like they have asymptotes. But they will not have any horizontal asymptotes, meaning that you should always get positive or negative infinity. You also should always get opposite answers. You will not have a log unless you've got something crazy like an x squared or something weird on the inside, which is not something I'm going to give to you. You will not have a log where you get both positive infinity or both negative infinity. They're always going to be opposite. So that can be a hint to you as well. So for B, for my left statement, I need to do the limit. What do I need to put underneath it? X approaches what? 0 from the right. And of f of x, h of x, actually, they're calling that one h. Change that to an h. Okay. As I approach 0 from the right, what's happening to my y values? Positive infinity. It's going up forever, right? The right side is going to be limit as x approaches positive infinity of h of x, and as I go this way, I am decreasing, so I will get negative infinity. Plus, since I got positive infinity on the left, I'm going to get negative infinity on the right. They're always going to be opposite. All right, another thing you're going to see is you're going to see these without a graph on calculator inactive, so we have to know what this looks like. Okay, so if I have log base 3 of x, your base does affect your graph. Let's look over here at Desmos. It's helpful to see. Your base does affect your graph. Y equals log base b of x. I'm going to put it in a slider right here. And I don't want the base to be 1. All right, so my base right here is 1.4 right now. So that base does affect your graph. If you look, it does affect it. Does it move our asymptote? Does it change our end behavior? Yeah. Yeah, we've not been interrupted nearly as much in the last month, yeah. Yeah. No, definitely nobody out there on the roof. So if you get bored. Yeah. Yeah. All right. So it does not change our end behavior. It does change our end behavior if we go over to here. It won't even let us do a negative. But if I go over here and get a fraction, it does change it because it's like negative exponents. And I don't think you're going to see a fraction base, but it does change some stuff. But if we're just talking positive numbers, it does not change our end behavior at all there. So what we've got is we also have this 2 out front. What's that 2 going to do to our graph? I'm multiplying by 2 out front. Vertically expand it. It stretches it up taller, right? If we go over here to Desmos and we put an A out here and we add that slider in, as that number gets bigger, it stretches it out. Does that change your end behavior? No. It changes the numbers you have. Both of these two things change the numbers that you have and how steep your graph is and all of those things, but it does not change end behavior of the graph. So we're looking at a pretty basic log right here. It has been stretched out, so maybe we'll make it a little taller looking, but it is still going to have a vertical asymptote right here, and the end behavior is not going to change. So if we're doing end behavior for this one, we would just do limit as x approaches. On the left side, we don't do negative infinity. We do 0 from the right. This is only for logs because they have those vertical asymptotes of g of x. And what am I going to get on the left side? Negative infinity, because that left side is going down. And then on the right, I will have the limit as x approaches positive infinity of g of x. And what do I get there? Positive infinity. Very good. Okay, questions? It's important to have that shape in your head because you've probably not done enough with logs. Like when I say quadratic, you're probably picturing the U shape in your head. You've seen those enough to know. At this point, I'm not sure you've done logs enough to know what that graph looks like. But it's something we are going to be expected to know. So it's something we need to be able to picture now for that. All right, so logs are always increasing or always decreasing. They're always concave up or always concave down. So they've given us just a couple pictures here. Let's see. Ethan, on A, is that graph concave up or concave down? It is concave up. Is it increasing or decreasing? Decreasing. Very good. Okay. Alyssa, for B, is that one concave up or concave down? Concave down. Is it increasing or decreasing? Increasing. Right? So you're just looking at which way it's curved, and if it's going up or down, always think left to right on that. Now, here's another one. This one does not have a graph with it. So we've got, and it is going to be on calculator inactive whenever you see this. So, log normally looks like this. The base doesn't really change that a lot. It kind of squishes the inner out, but it doesn't change that a lot. So the base is not a big deal unless you have a fraction or a negative, which I don't think you're going to see. But this -4 does affect our graph. What is it going to do to it? It's going to flip it. It's also going to stretch it, but is the stretching going to affect the end behavior? No. But that flip is going to make a big difference, right? So whenever it flips it here, we're going to have that point right there to say the same. We're going to have something like this. Still a vertical asymptote in the same spot, right? Let's see. Anaya, what's our concavity on that red graph there? Concave up. And are we increasing or decreasing? Decreasing. Okay, so it's all really in being able to picture what that graph looks like from the beginning and know about your transformations for that. Okay, here's another thing that they're going to ask us to do in this unit. They have given us a table, and it says selected values of several logarithmic functions are shown in the tables. For each table, find the value of the constant k. So they're telling us these are logarithmic, so we know that's the case. And then they're asking us to find these missing values that they've left off the table. So on this first problem, remember with exponentials, our x's have to be going up by equal intervals. Our y values have to be multiplied. That switches with a log, right? So our x's have to be going up by equal intervals, and you can see right here we're just going up by 1, and this is one of those weird ones that won't let me write. So you're going up by 1. I can't write it down. What's happening over here on the left side? Times 2. What would the k value be? 4. For that. So on g of x, you always want to check to make sure your x values are increasing at equal intervals, and they are on this one. What is happening to our numbers on the left side? Times 3. 6 times 3 will give me 18. 18 times 3 will give me 54. I'm pretty sure 54 times 3 is going to give me 162. What am I going to do to get k in this case? Divide by 3, because I'm going backwards. So if I do 6 divided by 3, I will get 2 for that. Okay. All right. H, we're going up by tens over here. I got 4, 5, 7, K, 19. Ooh. I mean, to get 4 times 5, it'd have to be 5/4, right? So, like, if we're trying this, and this would probably be no calculator, I would say. If I'm doing 4 times 5 over 4, that would give me 5. But if I do 5 times 5 over 4, that would give me 25 divided by 4. That's not 7. Okay, how are you, for this number right here? All right, how'd you get 11? Okay. Okay, so it will not let me write this here because it's evil. But if you see what Granger's saying here, we're going from 4 to 5, we went up by 1. Right? From 5 to 7, we went up by 2. And then yeah. So what's happened here is much like we did with the exponentials, this has been shifted up or down. So we don't have a number that we can just multiply by. But what we should see is an exponential pattern in those numbers that we're increasing by. So if this goes up by 1 and this goes up by 2, this should go up by 4 and then by 8. And if we check that, I'm gonna have to write it down here because it won't let me write up there. So if we go up by 1, up by 2, up by 4, and then up by 8, well, that would make this 11. K would be 11, right? And then 11 plus 8 would give us 19, and that would work. So although this is not just a straight logarithmic function, what's happening here is this has been shifted up or down. So it's got like probably like a plus 3 on the end. Is it 4? It's added something on the end, right? But we could still find that K, and it would be 11 for this. All right, this one's tricky too. We are increasing by 7 over here on the right side. So it's okay to look at this graph. We haven't skipped any values or anything here. What are we multiplying by each time? We're going from e to negative 2 to e. Or we're going from e to the 7th to e to the 10th. Okay, so we could kind of just look at the pattern for the exponent and see if that'll work for us. Negative 2 to a 1 that we have right here. And then we could go 1 to 4, and then 4 to 7, and 7 to 10. That works. We're really just adding 3 to the exponent. Here is why. Because what we're doing is we're doing e to the negative 2 times e to the 3rd power. And when you do e to the negative 2 times e to the 3rd power, you would just get e to the 1st power, right? And then if we take e to the 1st power and multiply by e to the 3rd, then we would get e to the 4th, right? So that's what we would be looking at there, that k. I know this is a mess because it won't let me write where I'm wanting to write. K is going to be e to the 4th power. And then if we did e to the 4th times e to the 3rd, we'd get e to the 7th. So that question, you are just looking at the pattern with the exponents. Because it's the exponents changing linearly and not the whole value, it is still being multiplied, right? You're multiplying by e to the 3rd. There. Okay, questions on those? All right, one more thing we're going to talk about is domain and range. So it is key to remember that log base b of x whenever b does not equal 1 and it has to be greater than 0. Greater than 1 for that. I don't think you'll see anything different than that. So whenever we got y equals log base b of x, the domain for that is it's got a vertical asymptote. So you can't have anything lower than 0. It's going to be 0 less than x. No, I'm sorry. It's going to be written this way. Sorry. You don't usually put infinities with that. It's going to be written probably this way. It's probably going to be written x is greater than 0. It does not have an or equal to, because a vertical asymptote you never actually reach, right? Or it might be written this way, 0 to infinity. Could be either one of those. And your range for that basic log function is negative infinity to positive infinity. There is nothing you can do to change the range on these functions, right? If you flip them, it's still negative infinity to negative infinity. If you stretch them, it's still negative infinity to negative infinity. You can slide them right or left. You can slide them up or down. You can do anything to these graphs. It's not going to change their range. So for all of these, it really does not matter what happened to our x values whenever, like, for example, A, what is happening with this 2 log base 3 of x? What's that 2 do to the graph? It stretches it out, which means we should be taking our range and multiplying it by 2. But when your range is already negative infinity to positive infinity, when you multiply that by 2, it's still just negative infinity to positive infinity. So this is going to be negative infinity to positive infinity. This is going to be negative infinity to positive infinity. This is going to be negative infinity to positive infinity. Right? Even flipping it upside down, it changes your end behavior a lot. But it still doesn't change the fact that the highest you go is positive infinity, the lowest you go is negative infinity. So range, pretty much always negative infinity to positive infinity for these problems. What does that tell me about the domain of exponentials? If range of a log is always negative infinity to positive infinity, what's the domain of an exponential? Negative infinity to positive infinity, right? Because since they're inverses, their domains and ranges are just switched. The domain for a log is typically 0 to infinity. Will stretching it out do anything to move that vertical asymptote? It will not. It does not move the vertical asymptote. The only thing we're doing right here, this is a vertical expansion by a factor of 2. It is not going to change our domain, right? So our domain is still 0 to infinity. Okay. The stuff on the outside affects the graph vertically, right? So that shifts it up or down or stretches it vertically. Do either one of those things change where a vertical asymptote is at? Vertical asymptote is this vertical line. If I move it up or down, it stays right where it was, right? If I stretch it up or down, that vertical asymptote stays right where it was. So is this negative 5 right here going to affect our domain? It will not, because that is all vertical things. And the only way you can change the domain is to move that vertical asymptote or flip the function over the y-axis, right? So the only way you can change that domain is to move that vertical asymptote, and it's only going to move if you shift it left or right. So on this, that negative 5 does nothing to our domain. But what does this do to the graph, this negative 3? That moves that graph right 3. Now, is that going to do something to our vertical asymptote? Yes, definitely. It is going to move it to the right 3. So instead of having a vertical asymptote at 0, it's been moved to the right 3. So we're going to have 3 to infinity for that problem. Okay, C is definitely the hardest one. Does that 8 do anything to our graph? No, we can just ignore it as far as domain is concerned. Now, there's a lot of other things they could ask us about stretching it out that we would need to know about it, but for domain, does not affect it. All right, this is going to affect it. The stuff on the inside affects the x-axis, right? So it looks like it has been moved to the left 3, but it has not. It's not actually moved to the left 3 because this is in combination with that 2 that is in front of your x. So here's kind of what I like to do for this. My domain right here, whatever this was right here, whatever the x was, it had to be greater than 0, right? It is also true that whatever this is has to be greater than 0. Now, I could have done that over here as well. I'll show you in a second. So this is going to be a horizontal compression and a shift to the left. But those two things in combination are a little harder to see what's happening. So whatever is inside of a log has to be greater than 0. So this is the way I like to do this problem. 2x plus 3 has to be greater than 0, right? The stuff on the inside has to be greater than 0. And if I just solve that, I'll subtract 3. So 2x has to be greater than negative 3 and divide by 2. So x has to be greater than negative 3 halves. It ends up being this number over this number is what you're going to see every time. So my domain would be negative 3 halves to infinity. Let me show you over here. I could have done that on this problem if I wanted. It's just less necessary because I know that's just right 3. I could have said x minus 3 is greater than 0. So if I add that 3, x would be greater than 3, which is what I have for my